Anyway, I was saying that inter-procedural optimizations are getting more and more important as in modern software, programmers use more and more layers of abstractions, more and more smaller objects with a lot of methods, often result as a lot of template expansions. And they expect that their programs will not slow down because of this. They expect that they will work as fast as before, if not faster. And we now have to look outside of the scope of single functions to achieve that. In this talk, I will look at a selected few, but the majority of inter-procedural optimizations that we have in GCC, and what they do, and the basics of how they achieve what they do. But before that, we will have a look where they are, where they sit in the compiler. GCC compiler, just probably like any other compiler, can be divided into three parts. We have a front end, which is the bit that understands your language, whether it's C, C++, Ada, Fortran, or some other languages. And then you have the backend, which is the bit that understands your target architecture. It knows how the assembly looks like, what the registers are, what the instructions are. It can emit the assembler. And it also contains some specific passes for any given architecture. And in the middle, it's not really an end, but because everything else is called an end, this is called the middle end. And that bit contains the optimizations which are mostly independent of the source language and mostly independent of the target architecture and can be commonly used by all of them. Now, this picture might seem like everything until the end of middle end is target independent. That is not actually the case. So, I don't want to mislead you. So let me warn you that pretty much from the start, the various bits of the compiler do query the backend. Front end already needs to know how big an unsigned int is, whether it's a 32-bit or 64-bit or 16-bit even. During the optimization pipeline, various passes do query the backend, what the capabilities of the backend are, what are the capabilities of the vector unit, for example, how wide the vectors are, and so on and so forth. We will be mostly concentrating on the language-independent and target-independent middle end, and particularly on that tiny bit that is called IPA. The IP stands for inter-procedural. A stands for analysis, but it's really more than that. It's not just analysis, but often even transformation. And that's why this talk is called Interprocedural Optimizations, which stands for both. But before we get to them, we have to talk a little about link time optimizations, because it turns out that it is not only not enough to compile just one function at a time, but you actually often want to see the whole program. Just the compilation unit at a time is not enough, because people structure their code depending on the meaning of the code and not on the optimization needs, and that's a good thing. Good software engineering practices demand that. Nevertheless, you have to see the context for powerful optimizations, especially when functions are small. And all of the interprocedural optimizations that I will be talking about have been designed from ground up to work well with LTO. So let me talk for a while what LTO is. Well, actually, let's start with what LTO isn't. This is the traditional scheme of normal compilation of a project where you run GCC in parallel on your source unit. GCC always produces an object file, .o file, that contains almost the resultant binary, which just needs to be combined by a linker to do all the relocations and so on to produce your results A.out. But when linker sees the object code, which is basically already in the form of machine instructions, it is really too late to do most of interesting optimizations. And therefore, what we need to do is, when we invoke linker, look at something different. So in LTO mode, when you compile your source files with -flto, you will end up with .o files that to users look pretty much just like normal object files, except that they contain intermediate language. They contain representation of your compilation units in an intermediate form, which still has a lot of information that the compiler then can use for optimizations. It can, or it may or may not also contain the object, the standard object file sections. But when linker sees these .o files, it figures out, well, wait a minute, there's something that has not been completed yet. Let me load a dynamically loadable object that is called LTO plugin, which is loaded into the address space of the linker, but it is actually part of the compiler project, of the GCC project. And LTO plugin says, yeah, I know what to do with this. And it invokes GCC again, a special binary of GCC that does whole program analysis, that loads bits and pieces of all of the .o files, not all of it, because that might not fit into memory, especially if your project's big, but selected pieces, does analysis on the call graph of that represents the whole project, whether it is a binary, whether it is an executable or a dynamically loadable library. And it makes various decisions. What needs to be propagated where, what can be removed, what can be inline, and so forth. This is the only phase that is actually serial, that does not run in parallel. Before, you know that the green GCCs run many at a time with make-j some number. But then we do not want to do the rest of the optimization in a serial phase. So we partition the program into various partitions, which may or may not resemble how you originally divided your project into compilation units. And these partitions are then optimized independently, and the final assembly is generated for them. When the assembler assembles them, they are run through the linker again, and you arrive at your final binary, which is or should be much better optimized and much smaller even. By the way, this is how vast majority of OpenSUSE tumbleweed packages are now built. We believe we are the first real distribution to achieve that. We have disabled LTO only for, I believe, 80 packages out of several thousand. And so this technique is real. It is no longer a toy. It is actually used in practice. And we are very happy that after about a decade of development, we have achieved the production level of quality. So let's have a look back at how the LTO scheme of things affects the division of the optimization pipeline and how the compiler itself is divided. So in the blue box, you see the bits that are, from user's point of view, still part of the compilation. That's what happens when you run GCC. And that is definitely the front end, which has to understand the language in which you wrote your project. Then there are bits that are called early optimizations. Now, early optimizations already work quite hard to lower the level of abstraction of a program so that the inter-procedural optimization and inter-procedural analysis has an easier time understanding what happens in your functions. The early optimizations are classical optimizations that work function at a time, usually in topological order, so the leaves first, and the functions calling these leaves second, and functions calling them the third, and so on and so forth. Then first bit of IPA happens as the summary building of IPA transformations, IPA analysis, look into the functions, and they try to extract the bits that are important. As I said before, when doing the whole program analysis, we cannot load everything into memory because it wouldn't fit. You wouldn't be able to compile even GCC on your notebook probably. Whereas it should be definitely possible with the scheme of things as they are now. And so only the small bits are extracted. The actually important parts are analyzed and saved aside. Then everything else that is in the red box happens from the user perspective when you run the linker. When you run LD or gold, and behind the scenes you get the whole program analysis and partitioning and everything. The IPA bit is in a yellow box itself because that is in a different binary and it is the only serial stage. And after IPA does all its decisions, the late optimizations carry out those decisions, do the heavy lifting optimizations like vectorization, all the classical loop optimizations, and so forth. Then backend takes over, generates the assembly, and you arrive at the assembly file that then goes through the linker. One important thing that happens also with LTO is something that is called symbol promotion, which means that many symbols which without LTO would have external linkage, they would be visible from outside of the compilation unit, are actually local in LTO. In simplified C-speak, this means that things magically become static. And that means that we have complete control over such a symbol, over such a function, if its address doesn't leak, of course. And yeah, that's what I just said. And this is performed with exact information from the linker, even for C++ comdat symbols, if that's something that you ever had to worry about. These can also be privatized, which in turn can lead to things like speeding up of dynamic linking. When you dynamically link two ASO objects and each of them has their comdat symbol, this needs to be resolved at link time. But if they are privatized, much fewer relocations have to happen when you're doing the dynamic link, and this can speed up start of programs, loading of plugins, and so forth. With that, I think that we know enough to have a look at some of the inter-procedural analysis optimizations. IPA is the acronym that we generally use, and that's why you see it sprinkled throughout this presentation, even though it really means analysis, but we usually also talk about optimizations because there is a transformation bit. One of the more simple ones is unreachable code removal. So let's assume that you have a code like this. It is, of course, slightly simplified compared to what happens in practice. But let's say that you have that you call function handle_big index, and this is the only call and only use in your program that is called when an index is too big. Let's also assume that the early optimizations can figure out that limit is actually 64 or 65 or smaller, and that the option in which, or the condition in which you call handle_big index never happens. If without LTO, for example, if you were, if you diligently marked your handle_big index function as static, this function can disappear. With LTO, because of symbol promotion, even if you forgot to mark it as static, or you didn't do it deliberately because in some other uses this function could be called, for example, in some other project as well, but in this particular project, it is only called once. Even without declaring it void, the LTO knows about it and can figure out this is the only use. We do have complete control over the function, and if it's not necessary, we can remove it. This is particularly important for heavy templated C++ code, where instantiations of templates generate gazillions and gazillions of functions, which eventually are not really necessary for various instantiations for various types. What is even probably, yeah, so in some of the benchmarks, the drop of size of the resultant binary is really jaw-dropping. So in the spec 2017 Parest, which is a C++, I believe, integer benchmark. I'm not sure whether it's integer or floating point. And the size of the resultant binary or the text section drops to 20% of the original, and it's mostly because of removal of things that are not necessary in the benchmark. But it also happens in real programs. In Firefox, 10% can be usually removed with LTO when we do have the information about what is really local to the whole application and what is not. Apart from things that are sometimes called and sometimes not really necessary, and that's discoverable in at compile time, what can also happen, and what is very important, is that even if in the example above, the handle big index call is necessary, but the inliner decides to inline the function, so replace the call with the copy of the body of the function. It knows that, well, okay, that was the only use. That has been inlined, so the offline copy is not necessary. That can also be removed, which, if it is not a static function without LTO, we do not know. We have to keep the offline copy. That is also another way how simple promotion with inlining and unreachable code removal can result in significant size savings during the compilation. The algorithm is fairly simple. It basically is propagation of required flag. So we begin with functions that we somehow do need. For example, if f1 in this example is the main function, we usually need a main function in a program and cannot remove it. It can also be a function that is callable from outside of your final SO object, that is the public interface of the dynamically loaded library that you're building. And what can happen during early optimizations, and often happen, is that some calls basically disappear. We, at compile time, can figure out that they're not necessary. And then we propagate the required flag from the functions that we trivially know are required. In this example, it would be f2 and f3, because f2 is required and it needs f4. f4 would also get the required flag, and that's it. Everything else can be marked as unnecessary, and we can just remove it. Another optimization people generally do not talk about that much is automatic discovery and propagation of various attributes. I'm not sure if you are familiar with the more basic ones, I'd say, as attribute pure, const, malloc, or no return. Pure means that a function is really a pure function of its arguments. It doesn't even read memory. It definitely doesn't write to memory. It only arrives at its result value as a mathematical pure function of its arguments. Const function is something similar, except that it is allowed to read memory. And malloc is something that behaves as a malloc. No return are functions like abort that just never return. These are very useful sometimes for optimizing functions that call functions with these attributes, and that's why it is necessary to try and mark as many of these that do have these properties with these properties. And of course, this information then has to be somehow propagated to the users, to the callers of these functions. So let's say that function f4 is a pure function, and that f3 would also be, but it also calls f4, which means that it is a pure function only if f4 is pure. But because we know f4 is pure, we can also mark f3 as pure. And if both f3 and f2 are pure functions, they only work on their arguments and do not have any side effects and do not load memory, even f1 can be then marked as pure, and that everything calling f1 will know this is a pure function. It, for example, if it is called twice with the same arguments, it will always arrive at the same value, and so we can collapse those two calls into one, and so forth. If you do not want to use LTO for some reason, or cannot for some reason, and would still like to know whether you might want to be, whether you might help yourself a little bit by decorating various functions with attribute pure, const, malloc, or no return, there is the warning w suggest attribute, which tells you, hey, this function looks like something like a good candidate to be marked with malloc, for example. One of the attributes that are not talked about generally, but it is perhaps one of the most important ones, is no throw, which marks that a function doesn't throw, that cannot throw exceptions. And propagation of that in LTO can save up to 46 of exception handling information and exception handling code blocks, which saves a lot of code and allows for more aggressive optimizations in functions that then call these no-throw functions. Very similar propagation happens to estimated profile information. So that's when you do not build your project with profile guided optimizations, but rely on GCC estimating how likely it is that a particular pieces of your program are going to be executed. And if something is deemed very cold because it aborts the program, for example, then everything, calling that generally can also be considered cold, and this is also propagated from callees to callers. One of the more magical inter-procedural optimizations is identical code folding, which basically means that GCC looks for functions that do the same thing. We say that they have the same semantics, that they are semantically identical, and we fold them, which basically means we turn them into one. So when we have two functions that do the same thing, like in this example, bar1 and bar2, GCC can discover that and just say, well, I can only leave one function in place and replace the other with just an alias of the first one. This works also when such a function calls another. So when two functions are the same and they call functions that are the same, they can also be considered the same. Note that these are not static functions, and let's assume that their address is taken. So even in LTO, they are not local. Someone somewhere took their address, which means that if those addresses are compared, they have to yield a false. Like for equality, the result has to be false. Therefore, they do have to have different addresses. So they are not merged with an alias, with an assembly alias of one symbol with another, but with a tail call. Basically, function foo2 is replaced with just jump to the semantically identical one. The algorithm, again, the details can be quite devilishly complicated, but the overall idea is not that difficult. What happens is that during the compilation phase, we calculate a fingerprint or hash, if you like, of each function. Then if two functions have the same hash, we actually load their bodies and then we compare them in more detail. And that if they look semantically identical themselves, we then have a look at what functions they call, and of course require that these have to be semantically identical, that these have to have the same meaning in the program. So in the example on your right, let's say that, that's supposed to be F1, G1, sorry, and F2, G2, F3, and G3. These pairs are considered to be identical, but we unfortunately realize that down at the bottom, F3 calls F4 and G3 calls G4, but G4 and F4 are not the same. They somehow differ, unfortunately. And then we have to go back and we have to declare F3 and G3 different, F2 and G2 different, and F1 and G1 different. Of course, if in some other case we have more luck and we actually figure out that the whole chain matches and H1 through H4 is the same thing as F1 through F4, we can declare all of them as the same and use the mechanism I described in the previous slide to basically merge them and save some space. Again, this is particularly important for C++ heavy code, where you can end up with through template instantiation in loads and loads of functions that are actually essentially doing the same thing. One of the other things that we do, of course, is propagation of stuff. Propagation of stuff from callers to callees is done by a pass that, for historical reasons, is called IPA-CP. CP stands for constant propagation. And that is because historically it started as something that propagated constants. So in the simplest possible example, let's assume that a range of functions, f1, f2, f3, and f4, all call functions g, and they all pass 1 as the parameter. It seems that it makes sense to replace g with function g1, which would already know that, look, this parameter is actually not a parameter. The parameter is itself removed, if possible, from the program and from the call statements. But more importantly, G1 now knows that the parameter is a constant and can propagate that constant internally in the subsequent late optimization passes. It can use them in various loop optimizations, vectorizations, and so forth, where such constant can be very important. If it is, in fact, such an important thing, sometimes it pays off to clone the function. So we have a slightly different situations where, for example, functions f1 and f2 pass 1 as before to function g, but there are also other functions, f3 and f4, that pass something that is unknown for the compiler to g. But the parameter is very important. For example, it can be a loop iteration size, or it can be something that is called loop stride, which basically means how far apart different elements of the array that we process are. Which, if it is 1, that basically means that data lie immediately next to each other and can be much more easily processed through vector instructions, something very, very useful for later part of optimization of a program or of a function. And therefore, it really makes sense to make a special copy of G1 and just make F1 and F2 called that particular copy. It also knows how data travel through functions, if they do travel through functions. So if actually, in the case of F1, the constant parameter 1 originated from its caller, F0, and F1 that just takes its parameter and passes it to G1, if this parameter is actually constant 1, GCC can discover that and clone the functions appropriately. As I said, historically, this was only about constants, but now we propagate not only constants, but constants passed by reference or as a parts of bigger aggregates, even though the discovery is rather limited at the moment. It also propagates polymorphic call context for devirtualization. So if we know what class a particular object that is passed to a function is, we do propagate that, and if this means that it is clear which virtual function will actually be called at a point of a polymorphic call, we do propagate that, and we use it for cloning as well. The two last bits, value ranges, and which bits are non-zero, are not used for cloning, but they are propagated and can be very important as well. Value range, for example, is mostly important when we know that some pointer is not 0, and then we can eliminate or is this null checks in various functions. And the last one is important for alignment. If we know that the last 2 bits have to be 0, then we know the alignment of a pointer, for example. The algorithm, again, on the high level is not very important. We summarize behavior of functions. So first of all, we definitely look at what kind of stuff they pass in the arguments and how data travels through the functions. So we construct so-called jump functions. And if an argument is always the value of an argument of a call is always the argument of the formal parameter of the function, then that is also marked down, even if there are some simple arithmetic functions involved. So if it is the argument the function receives is incremented and passed to another function, that is also recorded and can be processed. And we also record how specific values of parameters affect a particular function. So if various bits of the functions are only executed under certain conditions, we do create special predicates and the estimated times and sizes of this part of the function is recorded as only necessary when a particular predicate evaluates to true. We use a very similar mechanism when the context of a function then affects how the expected size and speed of various statements in the function and so forth. We of course do also mark down such special important cases like are the loop strides and loop bounds that I was talking about in the previous slide. And then we propagate these known values or context information from callees to callers. In my example, it is always top to bottom. We estimate their effect locally and then propagate the global effect from bottom up, from callees to callers. And then finally, we traverse the graph again. And if something looks like a good idea, which basically means that a particular cost function set, yeah, this is bigger than 500, let's clone. We make cloning decisions, and of course we record the information that are always true regardless of call context. And then these are then saved in the instruction stream for later optimizations. One interesting example where this particular optimization matters a lot comes from benchmark MCF, also from spec in 2017, where this benchmark spends a lot of time in quicksort. And it has two callers of quicksort, and they sort different things. So they pass a different comparator function to quicksort. And it turns out it is really super useful to inline this comparator function, so either arc compare or cost compare, to the quicksort itself. This benchmark carries its own quicksort implementation, so that is possible with LTO. However, because quicksort is recursive, and there are two comparator functions, without deduplicating quicksort itself, you cannot inline both comparators in it, right? So what happens is that constant propagation realizes this and clones quicksort, which allows of inlining of either arc compare and cost compare to its particular quicksort, and this results in about 10% speed up of the benchmark. And it always breaks when constant propagation, for some reason, refuses to do the cloning right. Which brings me to inlining. Inlining is by far the most important inter-procedural optimizations. It, of course, can completely hide any abstract penalties by combining everything into one big chunk. And the algorithm is, again, there are many details, but from the high level, it is fairly basic. It is a greedy algorithm, and it picks the best inlining candidate and keeps picking the best inlining candidate as long as it can. So as long as there are candidates for inlining, and as long as compilation unit or program growth limits are not reached. The call context information is also used, so all the predicates or the special information about loop bounds and loop strides from IPACP is reused for inlining as well. The inlining metric is actually quite simple. It is saved execution time times call frequency, measured or estimated, divided by function growth and total growth. Total growth can be negative if this is the last surviving offline invocation of a function, but we do not want to get into negative costs, so there is a maximum of 1 and total growth. And you can get, or an inline candidate can get special points for various things that are good, like making a call direct, which allows for further devirtualization. Again, newly discovered constant iteration count, newly discovered constant stride, again, something that I covered when I was talking about IPACP, and there can be penalties. Inlining of recursive functions is possible. Recursive inlining is a thing, but often not very useful, so there is a penalty for that. Cross-module inlining also is slightly penalized. And not every function is an inlining candidate. If it is really big, then we never inline it. If it uses really lot of stack, we never inline it. The inline limit is softer for functions marked inline, and for functions where the estimated benefit is really big. So it seems like you can help the compiler by marking stuff inline, but I'll talk about that in a minute. Firstly, I will tell you that there actually are two inlining passes in GCC. One sits at the very beginning of the early optimizations green box, and it inlines all functions which are clearly good candidates. Basically, where the call would take as much time and space as the function itself, that gets automatically inlined, and it helps the early optimizations a lot because it allows them to see small bits, small but still much larger bits of the program. And again, it clears and removes a lot of the abstraction penalty early that is usually introduced by C++. But inlining of big programs is very difficult because there are just so many candidates that look as good candidates for inlining that if you inline them all, your binary size would explode. You would get Firefox. If you inlined everything marked inline in Firefox, the binary would be several times over bigger, and because it wouldn't fit in cache, it would be also smaller. And it is difficult at compile time, without further information, figure out why this shouldn't be inline when it actually looks, it's a small function and everything looks fairly good. So either you can be very careful with the inline word, and you can have a look using winline or info inline options, what exactly is inlined, and then somehow try and help the compiler. But at the same time, C++ makes it very difficult to be careful with inline because all functions that are actually defined within the class are automatically marked inline, and that confuses the compiler a lot, and the compiler cannot rely on this information as much as for C programs. So the best thing that you can do, if you can do it, is use feedback-driven optimizations, which basically means you run your program in a test run and measure how it behaves, and then compile it again with these measurements, and GCC, if your test run is good, knows which parts of the program are really hot, which parts of the program are really important to optimize, and which parts of the program are not that important and can be left alone. And this can have profound effect. If we have a look at spec 2017, spec int, this is spec score, so higher is better. And we take what happens at 02 as the 100. You see that at 02, if you just use LTO, you get a little bit of speed up. You also get a lot of space savings of text sections. So your binaries are much smaller, often, and faster. If you, of course, go with OFAST, the most aggressive optimization level GCC has, and you compile for native ISA, the optimizations become more aggressive and you get much more significant speed up. But if you actually go with just O2 and use profile-guided optimization or feedback-driven optimizations, the two acronyms mean the same thing, you get actually slightly bigger speed up. And of course, the best options are those that combine both techniques, because both LTO and PGO, those are the last two bars with the biggest performance. And the reason is that LTO allows the compiler to analyze and transform the whole program, and PGO can tell it what is important and what is not. So if you can, trying PGO for your programs is definitely very, very good for your performance, provided that you get the test run right. Now, in the last few minutes, I would like to talk about a new optimizations in GCC 10 about removal of unused arguments. This actually happens also in GCC 9 and previous ones. So if you happen to have a function which in its signature has an argument, but that clearly is not used. This is a C++ program, GCC, and you see that the argument doesn't even have a name, so it clearly, it is basically declared as unused. And it is useless. The function is static. In LTO, it's completely under our control, and even current GCC can remove it. Sometimes the situation is not so clear-cut. In the previous example, the programmer could have done it and probably should have done it. But in this example, all the parameters that you can see are actually used, but there is still one that is not used. But you cannot actually see it. This pointer of C++, this function internally, from just looking at it, you of course do not know, or sometimes cannot know what is member symbol and what is not. But in this particular case, nothing that is used in this function is a member function or a member variable. And therefore, this method could have been a static method. But why should the programmer bother with looking for what can be declared static and what not, and then possibly change it later if it turns out to be the other way around? When the compiler can do it, and the compiler in this case can make this and does make this a static method, and will remove this parameter, the hidden this C++ parameter. The situation can get even more complicated with recursive function. This is another example taken from GCC itself, where we do have a function that takes as a parameter information whether it is looking at is something on the left-hand side of assignment or not. It only uses that parameter to pass it to some helper function, which in turn calls recursively the first function with this parameter and itself with this parameter. So there is a lot of passing of this LHS_p parameter, but it is all totally useless, and the parameter can be removed. And with the upcoming GCC 10, which does removal of unused parameters when traversing the whole call graph, it will be removed. Similarly, for return values that are not necessary, again, the example is taken from GCC source itself. We do have in value numbering function visit statement, which returns true if the value number for the result of the statement has changed after the function processed it. And it diligently calculates this. It gathers the changed bit from all the helper function it calls. But it turns out that no user of visit statement actually cares about the return value. And it may be a good interface, we may want to keep it, but currently it is completely useless. And again, in GCC 10, the compiler will be able to detect this and make all these functions void functions and remove from it all unnecessary calculations of the return values. Very quickly, how this works. We, for all function, gather only tiny bits of data, and that is whether we can actually change the signature of the function at all, and whether the function returns a value, because of course we do not want to remove them from functions that do not return value, that are already void functions. And per call, we gather two other flags, and that is this return value ignored? And if it's not ignored, is it perhaps only used to construct the return value of the current function? So if you have a function that calls foo and returns foo plus 1, this flag would be set for the call of the foo. And then we traverse the whole call graph, as I said before. So if we know that the call in F1 and F2 both ignore the return value, and F3 is a local object which does not have its address taken or escaped, we can actually change F3 to be a void function and remove all calculations of the return value that is now unnecessary. Similarly, if the call from F3 to G4 only returns it uses the return value only to actually construct the return value of F3, which is now removed, and other calls of G4 also ignore the return value, we can remove the return value from G as well. We have to be careful about recursive bits, which means that we firstly have to be optimistic about them and say, yeah, it's probably not necessary. But then when we figure out that there is actually a call where the return value is useful and necessary, we have to be able to go back to the chunk of chunk of functions recursively calling themselves that are called strongly connected component in the graph theory, and actually propagate again change our decisions to the more pessimistic one and actually leave G4, G5, and G6 in this example with their return function intact, or return value intact. Similarly, I'm slowly running out of time, so very quickly, in simple cases, GCC can change big arguments into smaller ones if only small bits are necessary. So if only PL from a bigger structure P is necessary, the load of PL can be moved to the caller, and function process L only gets an unsigned L. And this can also happen when this is passed by reference in simple scenarios, which is more difficult to do, but at the same time, the benefits when it can be done are bigger, because if we, in the caller, this means there's one fewer address taking of a variable, and if we can remove all of statements that take an address of something, we can optimize that something, which can, for example, be an object, much more aggressively. We can split it into bits, we can do constant propagation on it, and so on and so forth. And with that, thank you very much, and I hope that I still have a few minutes, although not too many, for any questions. And of course, I'll be very happy to answer any questions later on. Yes, the question is whether we now have usable debug info with LTO, and the answer is yes, with the GCC, and I'm not sure, but definitely with GCC 9, and I believe also with GCC 8 already, you do have useful debug info. Before that, all debug info was basically as if the program was written in C. So if you had a C++ program, you were only able to see mangled names, and it was very, very user unfriendly. But the whole way of how debug info is dealt with in LTO mode has been rewritten, and with recent GCC, we definitely produce useful debug info, to the point that, for example, Python pretty printers of C++ STL library work. So you can print your vector with a Python script out of GDB. So there is definitely useful debug info. Thank you very much.